So আজকে P4 না
So I'm going to continue the discussion that we did start on the last class about photoelectric effect. To summarize what I discussed in the last class, quick summary. Light was considered to be a wave earlier, and then photoelectric effect got discovered, and experiments were done on photoelectric effects. The experimental findings could not be successfully explained by the propositions of the wave theory, or in other words, wave theory failed to explain the photoelectric effect properly. The experimental findings were that there exists a threshold frequency below which photoelectric effect does not happen at all, irrespective of the intensity of the source. Above the threshold frequency of the source, the photocurrent is directly proportional to the intensity. Observation 1. Observation 2, photoelectric effect was a instantaneous happening. If photoelectric effect is supposed to happen, which means that source frequency is above the threshold frequency, light would photoelectrons would be emitted immediately, not after a delay. Wave theory predicts that energy is given in a continuous form to the shell electrons. The electrons should absorb and store that energy over a duration of time, and whenever their stored energy becomes higher than the work function of the atom of the electron, then the electron would shoot itself out of the atom, become a photoelectron. So this would predict that photoelectric effect should happen at all frequencies, and there should always be some delay between the light being shined upon the metal and the photoelectron coming out. This was not the case. So quantum theory of light comes into rescue, proposed by Max Planck, used by Albert Einstein. The quantum theory of light proposes that light from a certain source does not come as a continuous stream of energy. Rather, it comes out as packets or pellets or blocks of energy. Each of these individual packet of energy is called a photon, or a quantum of energy. Quantum is just singular, quanta is plural. The individual energy of each of these photon is given by Planck's equation, E equals to hf. H is the Planck's constant, f is the frequency of the source, which means high frequency light sources give more energetic photons, low energy light sources give less energetic photons. What quantum theory proposes that whenever these photons hit one of the orbital electrons of a metal, the energy is given to that electron immediately, not over a duration of time, rather immediately. All the energy is supplied to the electron immediately. If the received energy is bigger than the work function, photoelectric emission happens immediately. The electron spends the required amount of work function amount of energy to make itself free of the atom, and the remaining energy belongs to the electron as kinetic energy. If the supplied photon energy is not higher than the work function, then the electron would simply go up in a higher shell, absorbing that amount of energy, and immediately come back to the lower shell, giving up that absorbed energy in the form of infrared radiation or heat. This will heat up the metal plate a lot, but no electrons would be released. So the quantum theory of light successfully could explain the photoelectric effect, where the wave theory could not. This is one important aspect of this thing. From this part, what comes by is the core discussion of the whole photoelectric effect. I'm going to write the photoelectric equation first. The energy of a single photon is given by E equals to hf. F is the frequency of the source. Whenever this energy will be fall onto electron, this energy can be divided into two parts. One part can be used as work function, which is a symbol of phi. This is a circle with a vertical line goes cross beyond the line. Plus we write Ke max. There is a reason why we write Ke max. A max এর পার্টটা আমি একটু পরে আলাপ করতেছি. Bear me with this one. So one way that I can explain this explanation is that, let's say there is a metal, for this metal, let's say the work function value is 10 joule. There is a light source from which photons are falling onto the metal piece. Let's say the frequency of this source is such that the individual photon has an energy of, let's say, 12 joule. Whenever one photon will hit one of the orbital electrons over here, electrons will receive this 12 joule, spend 10 joules to make itself free or work it as a work or use it as a work function, and the remaining 2 joule would be stored within the electron as kinetic energy. So you might wonder that only writing kinetic energy would suffice. Why write K max? What's the whole point of writing max? There is a reason for this. Reason is that if we consider the structure of a metallic bond or any solid substance, try to understand. Let's say this is a metal piece. Let's say photons are falling onto this metal piece. Now you have to understand, atom is mostly empty space, which means it is not essential or it is not obvious that these incoming photons will directly hit one of the surface electrons. I mean, there might be an atom over here, there might be atom over here, there might be atom over here. There are different layers of atom. I'm showing you a highly magnified view over here. This is not exactly how big atoms are with respect to a metal cube. So this is essentially highly magnified. So figure not drawn to scale. Bear with me. If the photon hits one of the surface electrons, then the electron can simply spend the work function amount of energy and come out with a perfect 2 joule of energy. So incoming energy from one photon was 12 joule. Use up energy as work function was 10 joule. So this was used as work function. And the photoelectron is released with a kinetic energy of 2 joule. This perfectly makes sense. However, because atom is mostly empty space, many of the photons which fall onto the metal piece are capable to penetrate through the first layer of the atom and eventually go hit up some electrons on the second layer or in the third layer, in the fourth layer, in the fifth layer of the object, of the metal piece. Whenever photoemission is about to happen from an underneath layer, not from the exact surface, let's say a photon comes in, penetrates through these layers because atom is mostly empty space, and hits up an electron at the third layer inside the surface. The work function of this atom is also 10 joule. So incoming photon has an energy of 12 joule. This electron over here will spend 10 joule of energy. Now, as it comes out of this atom, it has 2 joule of kinetic energy. That's true. But it's not free yet because it has to penetrate through these 2 layers of additional atoms to eventually get out of the metal block. So to make that penetration possible through those upper layers beneath which the photoelectric effect did happen, it has to spend some of its available energy. So out of this 2 joule of kinetic energy, which it had available exactly at this location, to penetrate these 2 layers, some portion of this 2 joule of energy would be spent or lost. So as the electron will come out from the metal piece, it will not have the entire of the 2 joule. Rather, it will have something less. Maybe it will have, let's say, 1.5 joule, assuming that half joule of energy was used up to penetrate through these 2 layers. This gives us the idea that if we shoot 12 joule worth of photons onto this metal piece, and the work function of this metal block is actually 10 joule, work function of the metal piece actually essentially means work function of the electron is 10 joule, which means to make one electron free of the atom, you need to feed that electron 10 joule of energy, which is a universal property for all the atoms of the metal block. This is without saying that this is like an inherent property for identical atoms. There is no variation for this. All the outcoming electrons from this metal block, not atom, from this metal block would not come with 2 joule of kinetic energies. Very few of them will come with 2 joule of energy, exclusively those who were created at the surface. However, photoelectrons, which are created somewhere underneath, slightly below the surface level, they would spend some of the kinetic energy to penetrate through the upper layer, and as they will be coming out from the metal block, they will have slightly less than that initial kinetic energy. This is why we use the term K max over here. So if somehow there is a mechanism, there is a way by which we can measure this. If somehow we could possibly measure up this kinetic energy, which of the individual kinetic energy of the electrons which are coming out of the metal piece by photoelectric effect, if we could somehow measure this up, we would not get all the electrons to have 2 joule of energy. Rather, very few of the electrons would have a kinetic energy of 2 joule. Most of the electrons, statistically speaking, will have an energy slightly less than 2 joule. So that's why we use the term K max. So take away from this equation is that if we feed the object E amount of photon, electron absorbs E amount of energy from the supply. It uses phi amount of energy for its freeing up for its liberation. Then the remaining energy it uses as kinetic energy and go out. Now you might wonder, what if we supply an energy over here of using a source of exactly 10 joule? What's going to happen at that case? Should we have free electron? Because if we supply with a source that gives up photons of exactly 10 joule, will we have observable photoelectric effect? Because if we supply exactly 10 joule, which is actually the work function amount of energy, or in this case, this is this amount of energy for which this amount of, if this is 10 joule, then this frequency is what we call the threshold frequency, typically labeled as F naught. Will we have photoelectric effect, or can we observe photoelectric effect? The answer is not very easily, but we can. If you wonder how, in this scenario, only the surface electrons will have 0 joule of energy left whenever they will be free of the atom. In this case, if we want to observe the photoelectric emission to happen, we have to somehow help those electrons to get off from the metal piece and get absorbed upwards. So which means somehow we have to attract those free electrons and somehow collect them by a negatively charged field over here. This is actually, it can be achieved by experimental mix setup. I'll show you some example afterwards. But this is going to be really rare, but it's not going to be essentially zero. You can have some electrons coming up for which you can measure this. But measuring the exact kinetic energy of an electron is very difficult. I mean, how do you measure the kinetic energy of an electron? I mean, an electron cannot be observed. A moving electron cannot be observed even more so. So you cannot use K equals to half mv square to measure the kinetic energy of an electron. That's absurd, because you cannot even see the electron, let alone measuring its speed to be able to apply the formula half mv square. So there has to be an alternate way or an indirect way to measure the kinetic energy of the electron. There has to be a way. That comes us to the idea of what we call a phototube. A phototube is not very much too highlighted concept in your syllabus, but I personally find this topic to be very inherently incorporated within this chapter, and I teach this to every batch. And some version of this concept always show up, not always, I mean, let's say quite a lot of times it show up in the experiments. So I'll show you an example for how we can actually find out the kinetic energy of those free electrons indirectly. So there is a mechanism for this. Before I get into that, I'll just hold up a second. I'll take your question. Let me elaborate this equation a little bit so that we can go ahead to talk about what I'm trying to get at. So if I take a bit more elaboration of this equation, I can write E equals to HF, and phi can be written as HF naught. In this case, F naught is the threshold frequency, or which is the starting frequency at which photoelectric emission happens, plus K max. I can write this as simply K max because I am trying to write K max. If I now subject K max out of this equation, I can have this equation. If I am subjecting K max, other than writing it in this format, I might actually show you the full breakdown over here. So if K max can be broken down as half into mass of electron into V max whole square. So this is the full breakdown of this equation. HF is the supplied photon, HF naught is the breakdown of work function, F naught is the threshold frequency, and and this equation. We can do multiple different math for relevant type of replacement, what we need to do for a given, depending upon what variables do we have, are we provided in the question. So this equation can be used in a lot of different forms. But we will be using this equation in our worksheet afterwards. Don't worry about that.
Sir, H-টা কি জানি ছিল actually?
Thanks, Constant.
আর ক্যাপিটাল ই তো স্যার হচ্ছে লাইক টোটাল এনার্জি ইন দ্য সিস্টেম নাকি?
বলো, বুঝলি?
ক্যাপিটাল ইটা তো টোটাল এনার্জি ইন দ্য সিস্টেম।
No, not in the system.
তাহলে
Photon. Energy of a single photon. Energy of a single photon falling onto the electron, this much is used as work function. This is the remaining kinetic energy. We are talking about this part. One atom, one electron, one photon coming with an energy of E falling onto the electron. My straight lines are a bit bent. This one is spending phi for its freeing up, and then the remaining energy is remaining as, this should be a plus sign, as kinetic energy. That's the idea. This equation represents the happening for the emission of one photoelectron. One photon coming in, supplying E energy to the electron. That electron is using phi amount from that E for its freeing up, which is the work function, and then the remaining amount is used as kinetic energy of the electron. বুঝছো?
স্যার এই প্ল্যাঙ্ক কনস্ট্যান্টের ভ্যালুটা কত?
এটা তোমাদের ফর্মুলা শিটে দেওয়া থাকবে,
ডেটা বুকলেটে।
হ্যাঁ, ডেটা বুকলেটে দেওয়া থাকবে, you don't have to memorize that. Abias, you had a question?
Sir, just a few points. Like F naught, is that the threshold frequency?
F naught is the threshold frequency, yes.
So any energy below 10 joules in this case would not trigger photoelectric emission.
Exact amount of 10 joule of photon energy would trigger photoelectric emission, but that can be only be visible for a very few cases, because this would liberate the electrons actually from everywhere on the metal piece, but the most of the electrons would still get absorbed by the metal piece. I mean, try to think about it. Once an atom, metal atom, actually loses an electron by means of photon emission, it becomes positively charged. So it has some inherent tendency to absorb up any free electron around. Maybe that exit electron or any other electron that is available around, because it has become positively charged momentarily. So if we feed exactly 10 joule, observing the photoelectric effect can prove to be pretty difficult, but it would not be impossible. By applying appropriate mechanism, we can see that even at supplying 10 joule worth of photons for that kind of source, we would be see some photo emission happening, not absolutely zero. But for that to happen, we have to help those electrons which are liberated from the exact surface to travel away from the metal block, so that we could absorb it in a negatively charged metal net or metal plate. So we have to somehow help those electrons to be separated from the metal block. They cannot do this on their own because they don't have any remaining kinetic energy. It is possible to observe, but there has to be some additional help mechanism provided to the metal block. Bucho ki bolche?
I see, sir, but I asked if the energy is less than 10 joules. But what happens then? Where does the energy go then?
What happens if
10 joule on the sir, less than 10 joules of energy?
If we give less than 10 joule, I should have discussed this. Thank you. If we give an energy, if we give a source where the individual photon energy is less than 10 joule, in that case, photo emission will not happen, period. No matter how much light source you set. What's going to happen, that electrons are going to jumping to a much higher shell, but not essentially to become free up. They'll travel to a much higher shell, but and eventually come back to the original shell, and the entire metal pieces gonna start heating up. Because whenever the electrons are supplied some energy, they will jump to a higher shell. Immediately they will give up that energy in the form of infrared radiation and eventually come back to their original shell. So that they will not be freed up, so you cannot have free electrons. So photo emission will not happen. But the energy absorbed by the electrons would be given up in some other form of electromagnetic radiation, which ultimately heats up the metal piece.
Sir, what if it is already in the in a higher shell, the electron?
শুভ একটু ওয়েট করো। Abias, do you have any further question?
One last, just two more things, sir.
Sure.
Are these the valence electrons that are being affected?
Yes, essentially outer shell layer electrons.
Okay.
Not essentially valence electrons. They would more likely to belong to the conduction band, or maybe the in between. Valence electrons are defined as something that is already within the hybridization, or that has been used to produce the metal covalent bonds. But they are really difficult to separate out, because in that case you have to separate them out from two different atoms, because those electron logically belongs to both of them. These electrons that we're trying to free out from absolute metal pieces, so there are practically no covalent bonds preferably. We are freeing them up from a single atom, and they should preferably be the conduction band electron. I mean, I cannot exactly answer your question in this manner, because I'm not very used to this question. But
Basically, delocalized electrons, sir.
Yeah, definitely delocalized electron. But one thing that I can tell you is that in this case, phi basically somewhat phi is equivalent to the first ionization energy of any metal specimen that you have read in your chemistry lessons. So the amount of energy that you need to feed to a single atom to liberate its first electron, not the second, not the third. So we are talking about the minimum amount of energy that you need to feed to an outer shell layer electron, so that it can overcome the attraction of that atom and become absolutely free of the atom. That's what we mean by the word work function. The minimum amount of energy that is required for that atom to become free of the atom, for that electron to become free of the atom. Sorry. Do that make sense?
I am. Yes,
Okay.
sir.
Yeah,
And just
বলো, আবিয়াস বলো।
we're assuming electrons are particles in this case, right?
Yes, that makes the understanding much too easier to understand. Don't consider electrons as waves,
sir,
although
thanks.
we are going to see Broglie equation after a while. We're going to talk about electrons behaving as wave as well. After a while, it will show up. But for the time being, yes, we're considering the photon as a particle. We're also considering the electron as a particle. Visualize them as individual particles. So that makes the understanding much too, or comprehension much too, what can I say, stable or logical. Yeah, Shubhro, you had a question?
স্যার আমি বলছিলাম স্যার, আমরা যখন যে মিনিমাম 10 জুলস অফ এনার্জি যখন দিচ্ছি, মানে দ্যাট ইজ দ্য বর্ডার লাইন এনার্জি, রাইট? তো ওইটাতে স্যার ভ্যালেন্স শেল, মানে একেবারে যেটা হায়ার এনার্জি শেলের যে ইলেকট্রনগুলো আছে ওইগুলো স্কিপ করতে পারে না এক সময়?
Yes, that's what I say, that we are trying to separate out the electron that is most loosely attached to the atom, which means the least amount of energy that you need to feed to the atom to get one electron out. Now,
ইজ ইট লাইক স্যার যে শেল অনুযায়ী হচ্ছে আসলে ডিফার করে এনার্জি, রিকোয়ার্ড এনার্জিটা?
Yeah, totally. I mean, you'd have different and pure metals. For example, zinc, iron, copper, let's say molybdenum or boron, silicon even, which is a mu metal. Not mu metal. This is what is it called? Semiconductor. They all have their individual work functions, and this is much more related to that exactly at which shell their outer shell layer electron naturally is located. Naturally is important, because what is
like the higher the shell, the less energy is required.
Usually yes.
Right.
Yes, usually yes, but then again, there can be other factors involved as well. Other factors involved in the sense that if you remember how the periodic properties of elements in the periodic table, if you go down a group, new shells are added. But if you go on the right of a period, no new shells are added, but number of electrons become higher, number of protons also become higher. Do you know that?
Yes, sir.
So what you need to understand, that if you go down a shell if you go down a group, essentially your work function will reduce, because the electron will be physically located further apart from the nucleus. But if you go along a period, logically speaking, the radius of the atom becomes smaller, because you have bigger number of electrons attracted by bigger number of protons. So what I believe, I'm not essentially sure by this, but what my logic sense tells me, I have to take this up, but I'm sharing my idea with you, is that along a period, I believe the work function should increase because the electrons should become closer to the nucleus. And along a group, the work function should decrease.
So did you say along the
Period,
yeah
horizontal
along
alignment, the electrons should be closer to the nucleus, so the work function should be higher because more energy will be required to free them up.
স্যার কথা কেটে যাচ্ছে আসলে
আমি তোমার কথা ক্লিয়ারলি শুনতেছি।
মানে স্যার আপনি বলেন যে along the period হচ্ছে
হ্যাঁ বলো, along the period,
মানে স্যার along the period তো সেম শেলই থাকছে স্যার, সো এনার্জি তো আসলে রিকোয়ার্ড আর বেশি হওয়ার কথা না। shouldn't it be the same sir?
it shouldn't be same because along the period the radius of an atom becomes smaller because you have bigger number of electrons getting attracted by bigger number of protons, so the shell size actually becomes smaller. That's the periodic property of periodic table.
জি স্যার, সো মানে আরো ফ্যাক্টরস মানে রেডিয়াসও একটা ফ্যাক্টর এখানে,
Hey,
এরকম আরো কিছু ফ্যাক্টর
exactly,
থাকতে
exactly.
পারে।
It's all about how close that outermost shell layer electron is from the nucleus is basically what determines its energy level or energy requirement. The closer it is, the more strongly it is attached, so you would require bigger amount of energy to make it free, and vice versa.
জি স্যার।
All right. So where is the okay? Okay. I might as well reduce this. Acha. I was talking about this thing, and I was talking about how could we possibly measure the kinetic energy of a single atom, a single electron. I mean, that can prove to be pretty insanely difficult. But it's not so. Scientists are smart people, so they found out a way to indirectly measure the kinetic energy of a photoelectron. There's a certain circuit for this. I would like to pull this up from here. I hope I can find this. Give me a moment. Might as well pause. Okay, so we're gonna send some light over here, and photoelectrons are gonna travel through, and as they will be flowing through this through from the anode to the cathode, because the circuit is now closed, they have to overcome the electrostatic repulsion or electrostatic opposition to reach to this plate. This will bring to the idea that because of this factor, that this electric field is now applied by means of the battery, all the electrons which could earlier reach to this negative plate will not be able to get back to this electric plate anymore. Let me show you what I mean. Let's say the amount of photon we are providing was 12 joule, work function was 10 joule. So let me write E equals to phi plus K max. Let's say the K max was in this case 2 joule. So maximum kinetic energy these electrons can have is 2 joule, but many of the electrons will not have that. Let's say earlier, all the electrons which had even the minimum amount of energy when the switch was open, they could actually reach to this plate and could produce a current through this microammeter circuit. Well and good. Let's say now we have applied a certain amount of voltage over here, and for these charged particles, namely electrons, to travel from this plate to this plate, they have to overcome a potential gap. That potential difference is basically measured by this voltmeter. So as we know that voltage is given by work done by charge, so work done can be given by voltage into charge. So in this case we can say if an electron, Q is replaced as electron, has to overcome a voltage difference of V, they have to do an amount of work of W. This work done will basically come from a fraction of the kinetic energy. Let me tell you what I mean. Let's say we have set a voltage of, let's say, 1 volt across these two plates. Let's say that currently the voltmeter reading is 1 volt. For this 1 volt, the product of 1 volt into the charge of electron, let's say 1 volt multiplied by the charge of electron. I'm giving you some numbers to give you some idea. Let's say that product is now 0.5 joule. Let's say, what would this mean? It would mean each of the electron which will be released from this plate, anode plate, as photoelectrons to travel to the cathode. You might wonder that why should they travel to the cathode? Can they travel in other direction? Well, the honest truth is they are being emitted in all directions. Certain portion of those electrons will be absorbed in the cathode. But earlier, all of them could travel. But now all of them cannot travel, because to cover this space in between these two anode and cathode plate, each of the electron now have to work an amount worth of 0.5 joule, which means they have to spend 0.5 joule of their own energy to be able to reach over here. This amount of gap is now currently work like a resistance, which is eating up 0.5 joule of energy from each electron. So electrons have to sort of like give a tax of 0.5 joule or spend 0.5 joule enough amount of energy to be able to reach to this plate whenever this voltmeter reading is 1 volt. This brings us to a pretty interesting idea. Mone koro, let's say whenever we are shining this light over here, let's say every second 1000 electrons are produced. 1000 electrons every second. Let's assume. Mone koro, ei 1000 electron moddhe, let's say 200 electrons were there which had an amount of energy that is less than 0.5 joule, because like I said that all the electrons will not be coming out of 2 joule. Some electrons will have 2 joule and most of the electrons will have a much lower amount of energy of 2 joule. If 200 electrons were coming out which had less than 0.5 joule, this is what's going to happen. They're going to start their journey towards the cathode, and as they will travel further, they will be slowly losing their kinetic energy, which means they're going to slow down. The amount of energy that they require to reach to this plate is 0.5 joule, but their initial kinetic energy was less than 5 joule, less than 0.5 joule, half joule. So as they will travel further, they will slow down, slow down, slow down. Somewhere over here or over here, their energy will be finished. The kinetic energy will be finished. And as a result, they will momentarily stop, and because of the repulsion force, they will travel back to the anode. So they will not be able to reach to the cathode as they would be able to reach earlier if this voltage did not exist at all. So when the voltage was not there, more electrons naturally would be able to cover this distance and it get absorbed over in this plate. But whenever we are applying this voltage, fewer and fewer electrons can reach. I'm using the word fewer twice because what I'm about to do is I'm going to slowly start to increase up the voltage. Now, if I now increase the voltage, let's say now I increase this 1 volt to maybe 2 volt, then this work will essentially become 1.0 joule because I'm just doubling the voltage. In that case, more electrons will be pulled back. So much fewer electrons will be absorbed over here. So what is the predicament here? What is it that we're trying to achieve here? As we slowly reduce the resistance of this variable resistance, more voltage across the cathode and anode of the photodiote will be applied. So required work done for each electron or required amount of energy each electron needs to spend to overcome this space becomes higher. As a result, fewer and fewer electrons would be able to cover this entire path because it would require more energetic electrons. So all the electrons, the number of electrons reaching to this plate will slowly become less, which means as we'll slowly increase the voltage reading over here, this micrometer reading for the same intensity of light, this micrometer reading will slowly go down. This is all about that we are stopping or we are prohibiting certain number of electrons to reach up to the cathode by increasing the amount of problem that they have to go through, by increasing the amount of energy they have to spend to reach up to the cathode. This idea ki bujha geche? Everyone, see if it makes sense and respond.
Sir,
Bolo.
স্যার যখন 1 জুল কনসিডার করতেছিলাম আমরা মানে পুরো অ্যানোড থেকে ক্যাথোড পর্যন্ত ট্রাভেল করার জন্য লাগবে স্যার মানে এইটা কি আমরা ধরে নিচ্ছি যে সাম ইলেকট্রনস উইল নট হ্যাভ 1 জুল কাইনেটিক এনার্জি দ্যাটস দ্য রিজন দে উইল ফল ব্যাক
Exactly. And that number will be definitely bigger than 200 because I assume that let's say 200 electrons had an energy amount less than half joule out of this 1000 electron which is produced every second. If I now bring out up to 1 joule, maybe 600 electrons would have less energy than 1 joule. I don't know the exact number, and this is not linearly related, not at all, because we're talking about random distribution of the electrons coming out from different inside layers of the metal surface. So there would be a number, but this would be definitely bigger than 200. So whenever we set this at 1 volt and the required amount of energy was 0.5 joule, 800 electrons on an average, let's say 800 electrons could make their journey. Whenever we increase this to 2 volt and the required amount of energy is 1 joule, maybe 600 electrons are absorbed back and only 400 electrons can make their journey, which means fewer electrons can eventually reach to the cathode, which means the current recorded over here becomes smaller. Does this idea make sense? Everyone, if you have question, ask me. This is
Yes, sir.
এই পর্যন্ত বুঝা গেছে কিনা যে কেন আমাদের কারেন্টটা কমে যাচ্ছে?
Yes, sir.
Sir, but sir, what can be the reasons behind the electrons not having that much kinetic energy? Like energy shell-এর ব্যাপার হইতে পারে এখানে নাকি অন্য কিছু ফ্যাক্টর আসতে পারে? Like the factors we discussed earlier, sir. ওইগুলাই
No,
আসবে স্যার
that's pretty
এখানে?
much it. As far as I am concerned, I know that much because that much is covered in your syllabus. If there is more factors involved, I don't know about that. They are not covered in your syllabus. There might be, but I don't know. As far as I'm concerned, there is none. It's all about exactly at which location or at which layer of the metal surface did that photoelectron get manufactured. That's what the factor is all about.
তো স্যার ওয়ার্ক ফাংশনের জন্য যে আমার যে যতটুকু এনার্জি লাগছে লাইক where is it stored? Is that stored inside the electron?
No. That amount of energy is spent to move from the outermost shell layer, original shell of the electron, to the infinite number of shell or become freeing effect. That energy is spent in that process to be free from the atom.
So is it emitted as a form of heat or light? এরকম কিছু কি emit করছে এটার জন্য like since it's doing some work against the attraction of the nucleus?
So your question is, where is this 10 joule energy is going? Ultimately, what is
Yes
the
sir,
fate of
এটাই
this
মানে
10 joule
এটার
energy?
ফাইনাল এটা কি?
I honestly don't know that.
Sir, that's like a bond breaking energy, isn't it?
Yeah, it's sort of a bond breaking energy, but what happens when the bond breaking is happening? What does that energy do ultimately? I mean, where does this energy go?
So it becomes from light energy into the energy which the electron uses to get out.
No.
স্যার
Oh,
স্যার যে ইলেকট্রন গুলো হচ্ছে মানে মেটালের মানে যেগুলো লোয়ার এনার্জি লেভেলে উপরের তো প্রবাবিলিটি কম না যে ক্যাথোডে আসার।
Acha, এক minute, hold up, fine, এক minute. Rafid, I don't know this answer, but I'll look up for it, and I'm not willing to do this in the class duration, but I'll try to get back to you that what happens to this energy. I don't know this answer right now.
Okay sir.
Okay, হ্যাঁ, fine, বলো. What is your question?
স্যার যে ইলেকট্রন গুলো হচ্ছে লোয়ার এনার্জি লেভেলে মানে মানে মেটালের ভিতরে আর কি, মানে আউটার শেল থেকে অনেক মানে ভিতরে আর কি,
হ্যাঁ,
উপরের তো প্রবাবিলিটি কম যে ক্যাথোডে আসার, কারণ এগুলো তো এনার্জি কম থাকবে যখন মানে বের হবে এখান থেকে।
perfect.
ঠিক আছে স্যার, থ্যাংক ইউ।
Sure. So as we are going to slowly increase this voltage, we're going to have less and less amount of current over here. So if we keep on increasing this voltage, there would come a certain value of voltage for which this current will just become zero. Just become zero. Making this voltage just become zero means that even the most energetic photons, electrons, even the most energetic electrons which are emitted from this plate could not could not reach to this plate. This is what we call the stopping voltage. This is actually a key term, scientific term, stopping voltage, labeled as Vs. And if we now write the product of this Vs, as far as our expression goes, because here I wrote that maximum kinetic energy of any electron can be 2 joule, any electron can be 2 joule. So for our experiment, the product of electrons charge into the stopping voltage, this will be exactly equal to 2 joule, which means if our voltage, let's say this voltage becomes, I don't know how much should I write? Maybe 3 volt. If the stopping voltage is 3 volt, It means exactly at 3-volt potential difference across the anode and the cathode, no electron, even the highest kinetic energy electrons, which means even the 2 joule energy worth of kinetic energy worth of electrons, photoelectrons, could not make their reach to the cathode. They could not. This is how we measure the kinetic energy of the electrons. And whenever we have this value, we can come to plot a graph. And that graph can look pretty interesting. So I'm going to write up this equation over here. And let's have a look. Phi plus K max. If I now subject K max from here, it's going to be E minus phi. So I can write K max as electrons charge into stopping potential. I'm replacing that value. Multiplied, which should be equals to HF minus phi. So now we can plot a graph of these two factors. So on the y-axis, we can plot K max, or we can also plot this product E into Vs. This is something that we can measure. Vs can be measured by experiment from this experiment, and E is a p-known factor. So we can essentially plot this as numbers because we can calculate this product. We cannot essentially observe the electron. Like I said, that we are not going to measure the kinetic energy of the electron by seeing them. We're going to have an indirect method to measure the kinetic energy of the electrons. This is what the indirect method is all about, that we are actually applying a voltage to stop those electrons and measuring exactly how much voltage is required to stop the highest kinetic energy molecules, and that's basically giving us that value. If we now plot this graph, you can see over here that, and on the x-axis we're going to plot the frequency of the light source. Frequency of the light source means here we're going to have a source. This light is going to come from a source, and the light frequency of this source is f. So let's say we're going to be able to increase the frequency. If we increase the frequency of the source, let's say for a certain frequency, this source was giving out photons of 12 joule. If we increase the frequency, this 12 joule will become higher. Let's say after if we increase the frequency, let's say this 12 joule becomes 15 joule for a higher frequency value of the source, light source. Then the scenario would be 10 joule plus 5 joule. ठीक ना? This would mean if we now increase the frequency of this source, suddenly the current reading would become increased, because now the electrons would have 5 joule maximum kinetic energy, where they have to spend only 2 joule. So more electrons can come by. Then again, we can once again increase the voltage further up, and eventually find out the stopping potential for this light source as well. So which means we can change the frequency over here and the voltage source over here to ultimately make this current flow become 0, and we can calculate the stopping potential. So we can actually, what we are trying to plot, we are trying to, our experimental outcomes are the frequency of the light source, which is a variable, independent variable, and the stopping potential, which is the dependent variable. So we are changing this to find out this. And the product of E and stopping potential gives us the kinetic energy, maximum kinetic energy of the photoelectrons. So if we do go plot a graph, you can see there is a minus phi. This graph is going to give us multiple straight lines for different frequency values. All of these lines are going to be parallel to each other, because all of these graphs, have a look, y equals to mx minus c. This is y, this is m, this is x, and this is c, which means if I extend all of these lines onto the negative y-axis, somewhere they're gonna cut. This is gonna be my threshold function. This is gonna be my work function for this metal. So if this is the graph for a specific metal, this is the work function for this metal, which is on the negative y-axis. This is actually energy axis, so this is perfectly perfectly workable. So this is joule, this is also joule. And for this metal, let's say this metal has a threshold frequency of, let's say, f1. So let's say I'm gonna label this as f1. For threshold frequency of f1, we're gonna have the photo emission happening from here. So from this point, at this point, we're gonna have zero current. If we increase the frequency a little bit, we're gonna have some kinetic energy. So we're gonna have some you're gonna have more kinetic energy of the electrons, which makes sense from that equation. I mean, if you increase the frequency of the source, you are providing more energetic photons, so that your electrons can have more kinetic energy after spending their work function amount of energy. So you're gonna get this kind of graphs. So let's say this is for metal A, this for metal B, this for metal C, and this is for metal FA, and then maybe phi A, and then if I extend this backwards, we're gonna get phi B, and so on and so forth. So that's the kind of graph that we can have. Interesting idea. all of these graphs would be parallel to each other because all of their gradients is a constant. That constant is the Planck's constant. Frequency in this case is the variable. Frequency in this case is the variable, which is the x-axis variable, and c is the y-axis intercept, which is coming on the negative y-axis. This is basically shown in that note that I pulled up. I hope I have it here. This is that graph.
Sir,
Yes.
is it like the more we increase the frequency, the more photon particles hit the uh, anode part, right?
No. The more
Did I
we
say
increase the
it the other way
frequency,
around?
the more energetic photons hit the anode part. More photons
Basically,
and more energetic photons hit are two different things. More photons hit means number of photons increased.
yes, sir.
More energetic photons mean individual photon have bigger energy amount. There is a difference. Words matter. হ্যাঁ বলো।
But sir, how is the energy increasing here? Like when we are increasing the frequency, like মানে প্রত্যেকটা ইন্ডিভিজুয়াল ফোটনের স্যার মানে এনার্জি ইনক্রিজ করে যেতেছে।
Yes, yes, precisely.
Is that happening because of the equation equals to
HF.
HF?
Yes.
Still sir, like মানে এটা ব্যাকগ্রাউন্ডে আসলে কি হইতেছে যেটা কোন কারণে এরকম হচ্ছে?
মানে what part of the frequency increase causes the photon's value to increase?
Yes, sir, energy value to increase.
I honestly don't know this. I did not study about that. There is definitely some physical explanation, but I don't know. Any further questions so far? Anyone?
Is there any way we can increase the number of photons hitting the anode?
Yes, we can. I'm going to talk about this right after. I'll pick that up. আচ্ছা এই পর্যন্ত গেল হচ্ছে একটা ফ্যাক্টর and then we're going to try to find out a secondary factor. I hope I don't want the search results. I hope I can find can I find that? Yes, this is the part that I start to get at. Hold on, এই জিনিস একটু পড়ো সবাই। আচ্ছা I'll read for you. Effect of changing frequency and intensity on photocurrent. So let's say আচ্ছা what I need you to understand that কই গেল ফিগারটা কই গেল এই যে এখানে এই কেসে এখানে এই microammeter or milliammeter, the current that it records is what we call the photocurrent, because this current is basically because of the electrons which are capable to pass through this gap, or the current that passes through the phototube. This tube, this evacuated chamber, glass chamber, is what we call the phototube. The current that passes through the phototube is called the photocurrent. So the current that is created because of light, so that's called the photocurrent. So that's how it works. So how this value of photocurrent will be affected if we consider to change frequency and intensity individually. So let me first give you an idea for what frequency does to a light source. Frequency causes each individual photon to become more or less energetic. There is a simple example that I usually give to the students to make it a better sense. This is something like this. Let's say you have a biscuit factory. And you are making let's say 1,000 biscuits every hour. If you pack them 20 pieces a pack, if you do them 20 pieces a pack, how many packets of biscuit are you going to produce every second? Anyone? আচ্ছা আমি 1 per second দিয়ে বলি। Let's say you have a biscuit factory that is producing 1,000 biscuits per second. You are packing them in 20 pieces of biscuit per pack. So every packet of biscuit is having 20 biscuits. So how many packets of biscuit do you produce every second?
50.
It is 50, right?
Yes.
Hold on. Bujo, 1,000 biscuits.
Yes, sir.
You're making 20 biscuits per packet, so you're producing 50 packets. Consider this as a light source. Let's say a light source is producing 1,000 joules per second. If you pack 20 joules per photon, if you pack 20 joules per photon, then you are going to be producing 50 photons per second. That's basic math. Let's say another light source, which has a slightly higher frequency. Let's consider that this second source has this second source has the same intensity, which means it has the same rate of energy output as the first one. This one produces, let's say, 100 biscuits per second or 100 joule of energy photons. So it still produces 1000 joules per second, but every photon now every photon has an individual value of 100 joule. So how many photons will be produced per second?
Sorry, 10.
It will be only 10, right? So get the difference. If both the sources have the same intensity, which means if they produce the same amount of energy per second, let's say both of these sources are producing 1000 joules per second, but one source has 20 joule worth of photons, so it is producing 50 photons per second. So total 1000 joule is distributed over 50 photons. Each photon has an energy amount of 20 joules. The second source having a higher frequency, but the same intensity, which means the rate of energy production is same. So it is also producing 1000 joules per second of energy altogether. But because it has a higher frequency, it is producing each photon those are 100 joule of worth, which means every second it will be only producing 10 joules of 10 photons, only 10 photons. So what I want you to understand, if two sources have the same intensity or power, if one of them has a higher frequency, the other one has a lower frequency, the one that has a lower frequency will produce bigger number of photons, more photons than the one that has a higher frequency. Higher frequency will produce fewer photons and lower frequency will produce bigger number of photons. এই কথাটা বুঝা গেছে কিনা?
স্যার আমি একটু কনফিউজ এটাতে।
এই ফিগারটা দেখো, this is what I'm trying to show you. Let's say this length of this rectangular figure, disregard the gaps in between. This is not an ideal figure, just trying to show you. Let's say each of these rectangular block represents one photon. Let's say we are considering three different sources. This is the lowest frequency, a bit higher, highest frequency. So in this case, this amount of energy was distributed over this number of photons. This amount of energy was distributed in this number of photons. The same amount of energy was distributed in this number of photons. The source that has higher frequency will produce individual photons of bigger size. So the number of photons produced per second would be less.
Yes, sir. তার মানে number of photons আসলে কমে যাচ্ছে with increasing frequency, isn't it?
Exactly. If intensity is equal,
intensity যদি same রাখি আমরা.
Exactly. So if you have multiple sources who have the same intensity or power or power per area, but the one that has a higher frequency will be producing fewer photons. Same amount of energy will be covered by less number of photons because each photon has a bigger size. It's like the biscuit example comes in like this, that if let's say if you are making biscuit packets of 20 biscuits worth, and in another case in a simultaneous factory they are making biscuits of 40 biscuits worth. So you are going to be producing double number of packets of biscuit compared to the second factory, because you are putting in 20 biscuits in one packet and they're putting 40 biscuits in 1 second, but both of you are producing equal number of biscuits every second. So which one is going to produce bigger number of packets? The one that is packing small. Do I make sense?
স্যার
হ্যাঁ, ফাইন, বলো।
স্যার আমরা যে ফ্যাক্টরি এক্সাম্পলটা দিলেন, এখানে তো আমরা নিজেরা হচ্ছে মানে বললেন যে একটা বক্সে এতগুলো আমরা নিজেরা বানাচ্ছি বড় বা ছোট, আর এখানে ফোটনস গুলা মানে কিভাবে বড় ছোট হচ্ছে?
Depending upon the frequency of the source. For example, a violet source, light source, will give you more energetic photons compared to a red source. মনে করো একটা ভায়োলেট কালারের লাইট সোর্সের ফোটনের সাইজ হচ্ছে মনে করো 100 joule per photon. If the source produces 1000 joule per second, it means every second it will be only producing 10 violet color photons. So the total amount of energy is 1000 joule. On the other hand, let's say if a red color source, which is a lower frequency, if a red color source produces 1000 joule per second, but each photon has a value of, let's say, 20 joule, then it will be producing 50 photons. বুঝছো?
এটা স্যার এই যেটা বললেন যে ফোটনের হচ্ছে মানে এনার্জি যেটা আগে ছিল যে আগে বেশি এনার্জি স্টোর করতে পারতো এখন হচ্ছে কম, এটা মানে এই অ্যাবিলিটিটা কোথেকে আসতেছে যে একটা হচ্ছে এনার্জি কম স্টোর করতে পারতেছে আরেকটা বেশি?
আচ্ছা, এই ফ্যাক্টরটা ডিটারমাইন করা হচ্ছে সোর্সের ফ্রিকোয়েন্সি, and what is the physical property that affects that thing, that can bigger frequency has bigger photon size or smaller frequency has smaller photon size. I did not describe this,
ও আচ্ছা স্যার।
but this was I take my word that higher frequency source will give you photons of bigger amount of energy equals to hf, and smaller frequency source will give you smaller photon size. Size in this case I'm meaning the energy amount.
হ্যাঁ, তার মানে হচ্ছে যেগুলো ছোট হচ্ছে যেগুলো হচ্ছে মানে বেশি প্যাকেটস অফ ফোটন আসবে।
Exactly, for the same intensity.
ওকে স্যার, থ্যাংক ইউ।
বুঝছো কি?
ইয়েস স্যার।
আচ্ছা, এই কথাটা কেন বলতেছি, because this leads to our second description. You have to understand one thing. Each photo emission, one emission of photoelectron is an outcome of one photon collision. একটা ফোটন থেকে যদি বাইর হয় একটা ফটোইলেকট্রন বের হবে। একটা ফোটনকে ইউজ করে তুমি দুইটা ইলেকট্রন বের করতে পারবে না। The equation E equals to 5 plus Ke max is applicable for one incident of photo emission, which means if we can supply, মনে করো, let me give you a physical example. I'm going to write this down to have you a better visualization. So let's say source red, let's say source violet. Intensity দুইটারই হচ্ছে 1000 ইউনিট, ঠিক আছে? I energy of photon which is equals to hf, এটা হচ্ছে মনে করো 20, এটা হচ্ছে মনে করো 100. So number of photons, I'm going to write this in full, number of photons per second, this is releasing 50 photons per second, this is releasing 10 photons per second. এটু তো বুঝছো। এখন মনে করো there exists a metal, যে মেটালের থ্রেশহোল্ড ফ্রিকোয়েন্সি হচ্ছে, সরি, ওয়ার্ক ফাংশন হচ্ছে মনে করো 16 জুল। এখন 16 জুল মানে হচ্ছে আমি এটা দিয়েও ফটোমিশন করতে পারবো, এটা দিয়ে ফটোমিশন করতে পারবো, পারবো না? পারবো কিনা?
Yes, sir.
বিকজ বোথ অফ দেয়ার, আচ্ছা এখানে একটা জিরো বেশি লিখে ফেলছি, একটা জিরো কম হবে এখানে। আমি দুটো দিয়ে ফটোমিশন করতে পারবো বিকজ বোথ অফ দেয়ার photons energy is higher than the work function. Which one will give you a increased number of electrons released per second? You have to understand that this source every second can release 50 electrons because each photon can release 1 electron. How many photons are you supplying? 50 photons. Each photon can give you 1 electron, which means from this red source onto this metal, if you shine this red light source onto this metal, you can release 50 photoelectrons per second. Whereas for the violet light, you can only produce how many electrons? 10. The difference is whenever these light source will hit the metal surface, the electrons which will be produced over here, their K max for these ones, the K max over here can be 4 joule only, whereas these electrons K max can be up to 84 joule. So the electrons which will be produced from this pair of mechanism, pair both I mean this metal and also the red light source, for this pair we can produce 50 photoelectrons per second, where the maximum kinetic energy of those electrons can be up to 4 joule, but we can produce 50 electrons per second, so we can have a pretty high amount of current. Compared to that, if we use this pair, the same metal with the violet source with the same intensity of 1000 unit per second, we are going to be having only 10 photoelectrons per second, whereas the kinetic energy, maximum kinetic energy of these photoelectrons can be as high as 84 joule. But the number of photoelectrons will be how many? 10. Can you produce more than 10 electrons out of this pair every second? Is it possible? I want you to appreciate that information.
No, sir.
Using 10 photons, you cannot produce more than 10 electrons. That's not going to happen. One photon, one photoelectron. That's it. So this tells us the idea that if multiple frequency sources, I'm coming to the decision line, so pay attention, try to understand. If multiple different sources, all of which are capable of, if we have multiple other sources over here, all of which are capable to produce photoemission, which means all of their frequencies are above the threshold frequency for a certain metal. In that case, the one that has the lowest frequency will give you the highest photocurrent, because the source with the lowest frequency, which is still capable to produce photoelectric effect, will definitely make more electrons to shoot off. With each electron, less amount of kinetic energy, maximum kinetic energy, but the number of electrons shot or the number of photoelectric effect happening would be higher compared to higher frequency sources, because the higher frequency source that you go for, you will have fewer number of photons released from the source for the same intensity, and one photon only can release one electron only. এই পার্টটুকু বুঝা গেছে কিনা দেখো. If you have any question, you ask me about it.
Sir, can you repeat this last line?
Sure, I'll say it again. If we have multiple sources, all of which, if we have multiple light sources of different frequencies, so একটা থেকে information মাথায় নাও. If we have multiple sources of light of different frequencies, all of which can make photoelectric effect on a certain metal, then the source with the lowest frequency among those will give the highest amount of photocurrent, because this will give out more photons compared to all the other sources, and one photon will release one
So,
photon.
sir,
The number of photons would be high, but each released photoelectron will have a lower maximum kinetic energy, but number of electrons released would be much higher. প্রত্যয় বুঝছো কি বলছি?
Ji, sir.
আচ্ছা, হ্যাঁ, কে যেন কোশ্চেন করতে
স্যার
নিয়েছিল?
তার মানে এনার্জি কি কোনো ইফেক্টই ফেলতেছে না ফটোইলেকট্রিক কারেন্টের উপরে?
What
The
do you-
amount of energy, sir.
The amount of energy
মানে
of what? The source or the photon?
স্যার ফোটনের যেটা,
Yeah, photon's energy is divided into two parts. Work
মানে
on
এমনিতেই তো স্যার ক্যাথোডে তখন রিচ করতে পারবে না স্যার, রাইট? সো কিভাবে কারেন্ট বেশি আসবে স্যার তখন? যদি এনার্জি লাইক কম হয় তাহলে ওই চান্সটা থেকে যাচ্ছে না যে নট।
Listen close. I said that we have multiple
Okay.
sources of equal intensity, all of which can produce photoelectric effect, which means in this case we have chosen metals, all of which can produce photoelectric effect. All of which. So we will, হ্যাঁ বলো।
হ্যাঁ মানে স্যার আপনি বলেন, সমস্যা নেই।
না তুমি বলো, সমস্যা নাই।
না মানে স্যার, মানে এখানে তাহলে আপনি বলছেন যে যেটা লোয়েস্ট ফ্রিকোয়েন্সি সেটা হাইয়েস্ট ফটোইলেকট্রিক কারেন্ট দিবে, রাইট?
Yes.
বাট স্যার এমন কি হওয়ার কথা না যে যেটার মনে করেন যে ফ্রিকোয়েন্সি হাই যেগুলোর, সেগুলো তো বেসিক্যালি স্যার মানে পার ফোটন স্যার এনার্জি কি বেশি দিচ্ছে না আমাদেরকে?
Yes.
So isn't that supposed to actually accommodate for the electric current? Like current তো মানে, কারণ স্যার দেখেন স্যার অ্যানোড থেকে ক্যাথোডে যেতে যে এনার্জিটা স্যার খরচ হয়, লাইক ওই এনার্জিটা তো কম হচ্ছে যেটার জন্য লোয়েস্ট ফ্রিকোয়েন্সি।
It is not the amount of kinetic energy that the electrons will have remaining that defines the photocurrent. Photocurrent is charged by time. Charge is number of electrons into charge of electrons. Electron charge to fixed. By having increased amount of energy of the photon, you can have a much bigger stopping potential. For this discussion, what is convenient for you to consider is that, let's say this part of the circuit is not there. Let's assume this part of the circuit is not there. Even the voltmeter is not required. we just have a simple connecting line over here.
স্যার তাহলে ভোল্টেজের কোনো কনসিডারেশনই আসতেছে না কেন?
আমি এই কোশ্চেনের জন্য ভোল্টেজের কনসিডারেশন করতেছি না, because I'm not I use the voltage consideration to come to this graph, and I moved on from this discussion. Now I'm only saying that if we have multiple different metals, we have multiple different sources shining on a single metal, which one will give us more photocurrent for the same intensity, irrespective of, without applying any voltage across them. You just have a panel piece,
আচ্ছা
you're
আচ্ছা
somehow measuring the current coming out of that photoelectric effect of that metal piece. So which pair of components, light source and the metal piece, will give you the highest amount of current? That's what I'm trying to consider here.
কিন্তু স্যার ভোল্টেজ অ্যাপ্লাই করলে তো আবার সিচুয়েশন চেঞ্জ হয়ে যাবে তখন,
Definitely.
আই থিংক। ইয়া, বুঝতে পারছি guys.
All right. Sajid, you are about to say something? Your microphone went off.
না স্যার আমি কিছু বলছি না।
আচ্ছা, বুঝা গেছে কি?
হ্যাঁ স্যার।
স্যার একটা কোয়েশ্চেন ছিল যে
বলো রাফিদ।
স্যার আমরা তো এখানে like we are considering that only one photon gives the energy to the electron, but what if like more than one electron simultaneously, sorry, more than one photons give the energy simultaneously? Is that possible?
That is not possible. I'll tell you why that is not possible. It is experimentally observed that, I mean, I'll tell you what is the experimental observation which leads to this decision. If more than one photon could energize a single electron, experiment should show us that even there should be no lower limit for the threshold frequency. The term threshold frequency shouldn't exist. I'll tell you why. Try to visualize. Let's say there is an atom, spherical atom. On top of the atom, there is an electron which is about to become a photoelectron. Visualize that. Let's say this one requires, and this has a work function of, let's say, 10 joule. Let's say we are shining light onto this metal piece that is sending out photons of, let's say, 4 joule. If multiple photons could work on a single electron, then this should have happened. One 4 joule photon hits onto the metal piece, onto this electron. The electron jumps to a higher shell, receives another photon immediately, jumps to another higher shell, so it reaches up to 8, and then maybe receive another one, and eventually goes out of the electron. So if one electron could be acted upon by multiple photons in its journey path going out of the atom, we could have photoelectric effect at any frequency. But experiment shows us that no matter how much intensity we provide, which means, let's say, if this electron requires 10 joule of energy, and we set out, we provide it with energy source of, let's say, 4 joule worth of photon, even if we set up hundreds or 1,000 of these sources shining light upon this metal piece, we don't get any photoelectric effect whatsoever. That's the experimental finding. This proves that whenever the electrons can only be acted upon, or the electrons will only receive the energy of a single photon only and exclusively only when they are at their original state. Whenever they have received their one electron in their original state and they have reached up to a higher shell, they will immediately give up that energy and come back to the original shell and be ready to accept another photon. In their energetic state, they will not accept any more photon, because if they did, then simultaneous happen or cascading effect could be possible, and we should have had photoelectric effect at any frequency, at any low frequency for that matters. Intensity would be the prime factor, not threshold frequency. This actually the way this is more what can I say, more constructed, in a more constructed sentence matter, it can be said that the duration for which the electron stays in the excited stage is 0. So if you think about it, I mean, the electron is its original shell. Let's say its work function is 10 joule, but it receives a photon of 4 joule, goes up to a higher shell, and immediately comes back to its original shell, giving up that 4 joule of energy, and now it's ready to receive one more photon. The duration for which it stays in the upper shell or in excited stage is 0 second, and it is an absolute 0 second. So it just pops there, gives up the energy, and eventually comes back. It cannot be acted upon by multiple photons, because if it did, then we should have fertility effect in even at a very lower frequencies with enough intensity, but that's not the case. Do I make sense?
Yes, sir. And so this means, sir, যদি আমি মানে if I have multiple sources aiming at that metal piece, তাহলে হচ্ছে still in that original state, the electron can only accept the energy from one single photon. Like
Yes.
বাকিগুলোর থেকে নিবে না।
No.
Okay, sir.
I mean, it's not essentially scientific, but one type of visualization that can actually help, that sometimes I give to the students, is that try to visualize the photons coming out of the source like bullets coming out of a gun. Let's say a machine gun is shooting bullets or photons onto a metal piece. So there is some gap between each bullet shot. This is not like a strip of bullet. This is a shower of bullet. There is physical gap. And before the second bullet can come and reach to the photon would have automatically come down back to its original state. So the photon would not stay there to be affected upon by the second photon. The electron would not stay in its excited stage to be affected upon by the second photon. It would immediately come back to its original stage, and then it can accept another photon.
স্যার আপনি কোন ইলেকট্রনটার কথা বলছেন, যেটা হচ্ছে মানে বেসিক্যালি এমিটেড হচ্ছে না
Yes.
কিন্তু এক্সাইটেড হচ্ছে আর কি, টু
Yes.
আ হায়ার এনার্জি লেভেল?
Yes.
হ্যাঁ, বুঝতে পারছি।
Rafi, তুমি বুঝছো কি বলছি?
জি স্যার।
I could not give actual answer to your question, the physical reason why this is like this, but I told you the experimental outcome which proved this behavior.
That's right. I get some sort of an idea.
Okay, beautiful. So this was the next thing. The following part that I would like to discuss is about
স্যার,
follow.
আপনি যে বললেন যে একটা ইলেকট্রন যখন যে মানে এনার্জি লুজ করে আবার যে প্রিভিয়াস সেলে ব্যাক করবে, তখন ওই এনার্জিটা কোথায় যাবে, মানে যেটা ছেড়ে দিছে?
এটা আমি এক্স্যাক্টলি জানি না। sorry, এটা জানি, সেটা হচ্ছে this will be emitted as infrared radiation or some sort of electromagnetic radiation which will be used up for heating effect of the metal cube.
Okay, sir, thank you.
To be honest, I can make it more plausible. This is the exact frequency of light which it emits when it comes back to its original shell. That is what we see in the flame tests in chemistry. Think about it. Sodium ions give golden yellow color, calcium brick red, potassium lilac, blah blah blah. Silver gives a bit apple green color, something like that. Where does this color actually come from? There is a thing. Whenever we heat up, let's say sodium atoms at a high heat, the orbital electrons absorb up heat energy from the heat source. Then they make a prominent jump. Prominent jump means most electrons do a single jump, or most electrons do the same jump. So they jump to a certain shell, absorbing energy, and immediately comes back to the original shell. Whenever they come back to the original shell, that absorbed heat energy is given out as electromagnetic radiation. For sodium, that frequency of light happens to give us a sensation of golden yellow color. For calcium ions, that jumping back and released energy of the electromagnetic radiation gives us the brick red color. So every sodium atom, outer stellar electrons, do this, but they continuously jump back and forth. Taking energy out of the heat source, they cannot be completely free. If you wonder, what if we give a very high heat source? Well, as far as I know, that heat sources cannot produce photoelectric effect. What heat sources can do is heat sources can make something into a plasma. It can totally break down the whole structure, but not essentially make this thing completely give up an electron. So energizing a single electron by a heat source, as far as I know, is not achieved by scientific process yet, as far as my knowledge goes. But I might not be complete on this aspect, but I'm sharing what I know. So what happens is that electrons go up by absorbing the heat energy, and almost nearly each electron who are susceptible to make this jump, they make identical jumps. So let's assume the photon that for let's consider on a single atom. Let's say for a sodium atom, let's say whenever the sodium atom's electron comes back to from the energetic stage to their original shell, let's say the given up electromagnetic radiation, that photon, I mean, visualize this electron jumping up to down to the original shell, and in this jumping process, one electromagnetic radiation / photon is coming out of that atom. Let's say for sodium, that golden yellow color photon, that energy is, let's say, 15 joule, which means most of the atoms of the sodium ion specimen, they will be jumping above and come back, giving up energy of 15 joules. I'm using the word most because all of them might not do that. Some of the photons might give us some other type of jumps. But that fraction can be very small, which can be lost within the observation. Let's say if 100 sodium electrons make their jump back and forth, maybe 90 or 95 of them make the jump worth of this 15 joule of electron. Maybe 5 of them makes smaller or makes bigger, which gets merged with that golden yellow color. So ultimately the golden yellow color basically comes as the prominent color out of this observation. Do you understand my point? Then again, if you mix up, let's say if you mix up sodium chloride specimen and calcium chloride specimen together and then heat it up, you should be having a combined color sensation of brick red and golden yellow both. You shouldn't get a single color sensation because that's how our eye processes color. It receives the photons and together it combines up a single color sensation. So we're not going to be seeing golden yellow and brick red differently. It's very much like if you mix up two colors in a palette, you get a combined color. So what is happening in a combined color? Each of the atoms are giving up their original colors, but whenever you are receiving a certain percentage of one color mixed up with the other percentage of the color, together they're giving you a sensation of a new color. So that's what you can get if you have a mixture of those. So whenever the electrons come back to the original shell, they give up the energy as electromagnetic radiation. They can go up in their original shell, they can go up in their excited stage, either by receiving photons or it can be supplied by heat energy. It is possible. আচ্ছা আমি অ্যাকচুয়ালি ভুল বলছি আমি একটু একটা ভুল বলছি providing electrical heat energy, it is possible to detach electrons, which is actually done in harmonic emissions. I said wrong. My brain just kicked me. Yeah, we can actually disassociate electrons by providing heat energy. That's called harmonic emission. We use this in cathode oscilloscope. Remember?
Yes, sir.
So with enough temperature, we can actually make the electrons separate. But in our flame test, we make sure that the temperature of the flame is within certain value so that it essentially does not make the detachment of the electron altogether. Rather, it comes back and eventually give us some specific color that we want to see. Yes. I'll take questions. বুঝা গেছে কিনা কি বলছি এতক্ষণ?
Yes, sir.
Yes, sir.
So that's another thing, and there is one more thing that I'd like to cover in today's class, then I might call it a day. The other thing is the
স্যার আজকে বাদ দেন
একটা জিনিস
Yes, sir. আজকে ক্লাস শেষ করে দেন।
একটা জিনিস পড়াই তোমাদের ছেড়ে দিতেছি। I'll make the notes and make them available hopefully before next class. With particle duality না। এই জিনিস
স্যার লাস্ট ক্লাসের তো P5 টা আপলোড করেন নাই।
আপ করছি একটু আগে।
আর স্যার যে ম্যাগনেটিজমের ওয়ার্কশিট গুলো
ম্যানেজমেন্ট ওয়ার্কশিটগুলো তোমাদের প্রিন্ট করে দিব, ডোন্ট ওয়ারি।
স্যার এখন দিলে স্যার এটা করতে একটু মানে তাড়াতাড়ি করা যায়, প্রিন্ট কবে হবে?
আমি পিডিএফ তাহলে আপলোড করে দিচ্ছি, সমস্যা নাই, ক্লাসে পর পিডিএফ আপলোড করে দিচ্ছি।
স্যার এই নোটগুলো কি আবার আপনি যেরকম করে দিবেন?
হ্যাঁ গুছায় বান্ডিং করে দিব।
ওকে স্যার।
আচ্ছা এই জিনিসটা একটু আলাপ করে তোমাদের ক্লাস ছেড়ে দিচ্ছি। This thing has a very high similarity to the idea of gravitational potential. Recall, what was the unique behavior of gravitational potential for which it is unique?
It's zero at infinity.
It was zero as infinity, and as we got closer it was negative, remember? So that same thing is considered for electrons energy level as well. This is a figure for the hydrogen atom, which is the simplest of the atoms, which has only one proton, nucleus, and one electron. So there is not much problem to deal with it. So we're going to only learn about hydrogen atom for our syllabus. not any more other stuffs. The way, I mean, whenever, think about it, whenever, try to visualize, let me draw, not visualize, let me draw. মনে করো, let's say this is a, okay, let's say this is a hydrogen atom, electron, আর এটা হচ্ছে তার নিউক্লিয়াস, আর এটা হচ্ছে তার নিউক্লিয়াস, ঠিক আছে? আর এটা মনে করো হচ্ছে শেল 1, এখানে হচ্ছে ইলেকট্রনটা নরমালি থাকে। Let's say this is shell 2, and then there is shell 3, and then there is shell 4, এরকম, ঠিক আছে? What I'm trying to show you already is that you can see that the gaps are decreasing. There's a reason for this. As you go further up in the shell, the energy actually becomes decreasingly less. So electron typically stays over here. This is shell 1, then you can go up to shell 2, you can go up to shell 3, you can go up to shell 4. As it goes further up, it will become loosely attached to the atom because it is at a more excited stage. So there essentially is a certain shell at which the electron becomes absolutely free. We call that shell number as shell number infinite, where the electron is no longer attached to the atom anymore. Physically, that distance is measurable, but at that shell, the electron is free. Hydrogen atom has become ionized, which means the electron has left from the atom. By definition, at this stage, when the electron is free from the atom, we have defined that the electron has an energy of 0. This is the part very much similar to gravitational potential, that whenever there is infinite distance between two masses, then we can say that dp in one of the particle is 0 because there is no attraction. Force is 0, which means energy is also 0. But as they will become closer, they will be losing energy.
Sir, are we considering the structure of an atom here, right?
একটু শেষ করি, তারপর কোশ্চেন এসে শুধু হাত উঠাও। So as we are getting closer, the potential will become negative because they'll be losing energy in the process of getting closer. So whenever the electron is located at an infinite distance or really far away from the atom, we are considering the energy of that electron to be 0. It means definitely at the inner level, the exact energy value should have been negative, because you have to understand, এখান থেকে এখানে উঠতে এনার্জি ফিড করতে হয়েছে। So some addition of energy gave rise to this, some addition of energy gave rise to this, some addition of energy gave rise to this, eventually some addition of this gave rise to this. It is not essential যে ইলেকট্রন সবসময় এভাবেই ট্রান্সফার হবে। Electrons don't have to, electron might as well transfer from here to directly outwards as well in a single jump. That's also possible, but that's not my point. My point is that to reach from n equals to 1 to n equals to infinite, you have to give energy. So here is the initial value. You add some energy, positive energy, let's say maybe 10 joule. I'm just assuming this number, and then the energy becomes 0, which means this number has to be how much? Minus 10 joule. Because at the infinite shell, we are defining the energy of the atom to be 0 joule. This is the similarity which you have to see at this figure. This is a bar diagram, sort of like only a linear diagram, but in the vertical axis. There is no horizontal axis. So this is just a vertical number line sort of thing. This shows us the individual energy value of the hydrogen atom. This is where we consider the energy to be 0, which means no, this is not 0. 1 2 3 4 5 6 2 3 4 5 6 okay, হ্যাঁ ঠিক আছে, বলতেছি এখানে কি হইতেছে অ্যাকচুয়ালি বলতেছি। হ্যাভ এ লুক। Okay, can I see the whole figure somehow? 750. Okay, and yes, if you have a look, this is the shell number which is defined as n equals to infinite. At this level, the energy is defined to be 0. Right below this, the marked shell is this one. এই এনার্জি শেল এর ভ্যালু হচ্ছে এটা। হ্যাভ এ লুক, এটা ভ্যালু হচ্ছে এখানে, এটা ভ্যালু এখানে, এটা ভ্যালু এখানে, এটা ভ্যালু এখানে, এটা ভ্যালু এখানে, আর এটা ভ্যালু হচ্ছে 0, which means this is your shell number 1, this is your shell number infinity. Here the shell number has some negative energy value, and here the energy value is 0. So further, as you further go down from the infinite shell downwards or closer to the atom's nucleus, you have more increasing negative value for that shell, which means the first shell has a energy value of minus 13.6 electron volt. What does this number signify? This number signifies that if we want to liberate an electron from its first shell all the way up to the infinite number of shell, or altogether make the electron release, we have to feed that electron minus 13.6 electron volt. Taking this much energy, the electron can become free of the atom. Minus 3.4 means the distance between these two. This line and this line has an energy difference of minus 3.4. Minus 1.5 means this line and this line has a difference of 1.5 electron volt, so on and so forth. So what happens whenever, if we give some energy, if we give an electron a certain amount of energy, electrons will only make their upward jump in a single step, but they can make their downward jump in multiple steps. আচ্ছা, এই জাম্পিং এর পার্টটুক নেক্সট ক্লাসে বুঝাবো, বাট আপাতত এগুলা কেন নেগেটিভ হয়েছে এবং কেন ইনক্রিজিংলি নেগেটিভ হয়েছে এই কনসেপ্টটা বুঝা গেছে কিনা, হুইচ ইজ সিমিলার টু দা গ্র্যাভিটেশনাল পটেনশিয়াল, এটুক বুঝা গেছে কিনা?
স্যার
Yes, sir.
ঠিক আছে, জাম্পিং এর পার্টগুলো আমাদের পরে আছে, এই জাম্পিং এর পার্টগুলো এখানে আছে, জাম্পিং এর পার্টগুলো আমি এখান থেকে নেক্সট ক্লাসে বুঝাবো। আজকে এইটুকু পর্যন্ত থাক, আর তোমাদের ম্যাগনেটিজমের ওয়ার্কশিট মার্কস আমি আপলোড করে দিচ্ছি, ডোন্ট ওয়ারি অ্যাবাউট দ্যাট। গুড নাইট।
ওকে স্যার, বাই স্যার।